Now hopefully this should not stop in between. This is so frustrating, all of y'all. Again and again I have to start new streams. I know it is equally frustrating for y'all as well. Now let's just pray that this doesn't stop in between. Alright. Now without any further delay, I am going to start with question number 19th now. The speed of a wave on a string is 150 meters per second. So V is 150 meters per second. You all can switch on to full screen mode, guys. You all can switch on to full screen mode if you are watching it from mobile. And the tension is 120 newtons. Okay. The percentage increase in the tension in order to raise the wave speed by 20%. So V final is equal to V initial plus 20% of V initial, then percentage increase in tension. Percentage increase in tension is how much? Now students, understand one thing, that whenever we say percentage increase, it means you have to find final tension minus initial tension upon initial tension into 100. Whenever percentage increase is asked, you will find final tension minus initial tension upon initial tension into 100. This is nothing but percentage increase. You all understand this? Now, guys, what is the relation between V and T? Relation between V and T? So we can say that velocity is proportional to root capital T. So we can say V square is proportional to T. V square is proportional to T. So from here we may say V final square minus V initial square upon V initial square into 100. We have replaced T final with V final square, T initial with V initial square upon V initial square into 100. Now, it's time for us to substitute the values. So, V initial we know is how much? 150. V initial is 150. So 150 plus 20 into 150 divided by 100 is 180. This is 180 meters per second. This value is 180 meters per second. Now let us substitute the values. I'm going to erase this. So we can say 180 square minus 120 square, 120 square into 100. Now how do you simplify this, all of y'all? How do you simplify this? Oh, it's easy to simplify. It is easy to simplify this. A square minus B square. It is 180 plus 120 into 180 minus 120, 120, 120, 100. Now how much is 180 plus 120? 300 into 60 upon 12 into 12. Now 12 5s are 60, correct? 12 5s are 60. And 12 into 25 times is 300, which gives us the answer as 125. So, do we have such option? I'm getting the answer is 125. Now, what was the initial value, all of y'all? Initial value is 120 and now it has become 125. Have we done any mistake, all of y'all, over here? Oh, correct. I made a mistake, correct. Guys, I'm going to solve this question again, don't worry. Correct. The method was perfectly fine, but I substituted the wrong values. 19th question. The speed of the wave, V initial is 150 meters per second. Tension initial is 120 Newton. Percentage increase in tension, that is T final minus T initial upon T initial into 100 is equal to question mark. This is what we have to find. Wave speed should increase by 20%. So V final is 150 plus 150 into 20%. This gives us the answer as 180. This gives us the answer as 180. So we can say velocity is proportional to root T, V square is proportional to tension. So in place of TF, students, in place of TF, I am going to write VF square minus VI square upon VI square into 100. Now substitute the values properly. 180 minus 150 square upon 150 square into 100. This gives us the answer as 44%. Answer is option A. Option A. Correct. So guys, the method was correct. Just last time I substituted 120 over here. That's why it went wrong. It is 150 actually. Okay. Moving on to question number 20. Question 20. A wire of density, so rho is given to us as 9 into 10 raised to 3 kilogram per meter cube, is stretched between two clamps 1 meter apart. So length is 1 meter, is subjected to an extension small l. Ajay, this is Young's modulus based question, all of y'all. This question is Young's modulus based. Last time I told you that questions based on Young's modulus that we'll solve later on. I have told you this last time. So question 20 we are not solving. Correct? Question 20 we are not solving. 21, all of y'all. Come on, quickly. 21. The length and diameter of the wire is doubled. Length, diameter, both are doubled. Tension constant, material same. Fundamental frequency. Come on, students. Frequency is proportional to, or other formula is 1 upon 2L root of T by mu. Frequency will be equal to 1 upon 2L root of T upon rho A. Frequency will be equal to 1 upon 2L root of T upon rho into pi d square by 4. Because we want diameter. And now in terms of proportionality, I can say frequency is proportional to 1 upon dl. Frequency is proportional to 1 upon dl. So frequency nu will be proportional to what happens to the length becomes double and diameter also becomes double. So the new value of frequency becomes 1/4 times the original value, which is option 1. New frequency becomes 1/4 time. Correct answer, Kshitij. Correct answer, option A. All right. Question number 22. A 23 degrees Celsius pipe open at both the ends resonates at a frequency at 450 Hertz. So pipe is open at both the ends. Frequency is 450 Hertz and temperature is 23 degrees Celsius. At what frequency does the same pipe resonate on a hot day when the speed of sound is 4% higher than it would be at 20 dB? So speed of sound in second case is speed of sound in first case plus 4 upon 100 times the first case. 4% higher. 4% higher. So you have to find the frequency, students. You got to find the frequency. Come on, is the question clear to you all? Everybody? Now, let us try to solve this question. Let's try to solve this question. Now, how will you solve? First of all, you will say that velocity and temperature. Velocity is proportional to root t. Come on. Velocity is proportional to root t. Do you agree with this? All right. Now, the velocity change is only 4%. Vishaka, which part do you want me to explain? Vishaka, which part? Vishaka, which part do you want me to explain? The question. Okay, I'll explain the question. Don't worry. See, Vishaka, read the question. What does the question say? At 23 degrees Celsius, a pipe open at both the ends. You can see the pipe is open at both the ends. On the screen, pipe is open at both the ends. Resonates at frequency 450. Resonates means vibrates. Resonate means vibrate. So vibration frequency is 450 Hertz. And temperature is how much? 23 degrees Celsius. Temperature is 23 degrees Celsius. Then it says, then it says, at what frequency does the same pipe resonate? At what frequency does the same pipe resonate? On a hot day when the speed of sound is 4% higher. Speed is 4% higher, 4% more. So V2 is V1 plus 4 upon 100 into V1. I hope now the question is clear to you. Got it? Now tell me. Velocity is proportional to root of temperature. So we can use the error formula. we can use the error formula and we can say that delta V upon V into 100 is half delta T upon T into 100, correct? We have used the error formula, students. Now, change in velocity is by 4%, half delta T upon T. T is how much? 23 plus 273. You have to convert it to Kelvin, which is 296 into 100. So change in temperature is 8 into 296 upon 100. We can consider 296 as 300. So 8 into 300 upon 100. So delta T is 24. So temperature increases by 24 degrees Celsius. Temperature increases by 24 degrees Celsius. Is that clear? Temperature increases by 24 degrees Celsius. Now, tell me, what is the formula for frequency? Frequency is V upon 2L. Frequency is V upon 2L. Now, what do we have to find? We have to find the frequency. We have to find the frequency. So, I'm going to erase this and we can say that frequency is proportional to V. So, if V increases by 4%, frequency will also increase by 4%. So the final frequency will be equal to initial frequency plus 4 upon 100 into original value. Original value is 450. And when you solve this, you will get the answer as 468 Hertz, which is option 3. No submit, because of lack of space I cannot adjust my board or mobile. I just have a limited space option over here, okay? Now guys, just listen to this carefully. Listen to this carefully. All these steps that we have done, are not required, because once we get the change of 24, these steps are not required. We can directly solve it like this. Then you will ask that, sir, why did you solve this? I just solved this to explain to you all that in the same question, I can add one more sub question. Find the change in temperature. Okay. So if I add a question that find change in temperature, you will have to do all these steps. So in a single question, I have solved 2 sub questions. I am giving you all extra practice, all of you all. Because in NEET examination, question can be asked in any given format. So I hope this concept is clear to you. Yes, Aditi. We can do N1 upon N2 is equal to V1 upon V2. Correct. So students, did you understand why I have done all these things? Got it? It is for your own benefit. ठीक है बेटा? Moving on guys to 23rd question now. An observer moves towards a stationary source of sound frequency n, observer move towards stationary source. So we have a source which is at rest. We have an observer which is moving towards the source. It is sounding a frequency n. The apparent frequency heard by him is 2n. Velocity of sound is 332 meters per second. Then the velocity of the observer is, this is a very easy question. Apparent frequency is equal to V, observer is moving towards, plus V naught upon V. Source is stationary, the whole into n. This becomes 2n is equal to V plus V naught upon V into n. Cancels out. So V is equal to V naught. V is equal to V naught. The answer is option 3. Very good. Virat, Rugved, Atharv, Samir, Kshitij, all of you all, keep it up, beta. Last question, come on, I want to finish this question quickly and start with the new chapter. I'm going to increase the speed of solving. Come on, students. 24th. A source of sound S is moving with a velocity of 50 meters per second towards a stationary observer. Source moving with 50 meters per second. Observer is at rest. The observer measures the frequency. Observer measures means apparent frequency is 1000 hertz. What will be the apparent frequency of the source when it is moving away from the observer after crossing him? Alright, case 1, moving towards. Case 1 is moving towards. So apparent frequency of first case is V, observer is at rest, upon V, source is moving towards, minus Vs into n. Apparent frequency is 1000 of the first case is equal to V upon V minus 50 into n. So from here we can say n is equal to 1000 V minus 50 upon V. Okay, Shreya, I will answer your doubt after I am done solving this question. I will answer your doubts later on. Now case 2. Case 2. Source moving away. Come on, students. Apparent frequency is equal to V upon V plus Vs into n. V as it is upon V plus 50, and in place of n we will substitute this value 1000 into V minus 50 upon V, cancels out. How much is this, beta? 1000 into V. What is the velocity given? 350. 350 minus 50 is 300 upon 400. And answer to this question is option 1. Answer to this question, 24th question, is first option. Okay, now Shreya is asking us a doubt. Module 1. Now let me just check where the module 1 is. Module 1, question 11th homework. Page 75, question 11th. A vibrating tuning fork of 100 Hz sends out longitudinal waves in air. Then in a span of 10 seconds, a particle situated at 10 centimeters from the tuning fork will receive. Okay, how much is the frequency? 100 Hz. Frequency is 100 Hz. It means 100 compressions in 1 second or 100 rarefactions in 1 second. In a span of 10 seconds, how much will it receive? In a span of 10 seconds. Beta, in 1 second it receives 100 compression. So in 10 seconds, it is going to receive 1000 compression. Answer is third option. Answer is third option. It was just based on the definition. The question was just based on the definition. Now, any other doubts? Any other doubts, everybody? Can we start with the next chapter? Okay. Students, last time I'm asking. Okay, no doubts. Thank you, Virat, for the inputs. Okay, Aditi, Vishaka, all of y'all. If all of y'all are agreeing that you don't have any doubts, I will start with the next chapter. Okay, now Vishaka is asking us a doubt. 10th question, module 2 homework. 10th question, module 2 homework. Just when I was about to start the chapter, Vishaka asked the doubt. Great timing, Vishaka beta. 10th question homework, is it? Yeah, 10th question, yes. Which page number it is? 10th question. Yeah, got it. Page number 101. No problem, Vishaka, no problem. You can ask doubts, no problem. Two closed pipes produce 10 beats per second when emitting their fundamental notes. If their lengths are in the ratio 25/26. So L1 upon L2 is 25/26. Now frequency is inversely proportional to length. So N1 upon N2 is 26/25. And they are producing 10 beats. If they are producing 10 beats, then N1 minus N2 is 10. Now Vishaka, just look at this equation. Look at this equation. Two unknowns, two equation. Just solve them, you will get the answer. Solve them, you will get the answer. Now students, I'm going to give you all 30 seconds to think whether you have any more doubts or not. I'm going to wait for 30 seconds. Okay. Alright students, now I'm very excited to start the next chapter, which is wave optics. We are going to start with the next chapter, which is wave optics. Now Virat, you can solve that bit and get the answer. If you are not getting, please remind me towards the end, okay? I would now like to go with wave optics. Come on students. Now why I like this chapter a lot is because this is a beautiful chapter which is going to translate yourself from the chapter of sound to the chapter of light. I call this chapter as a smooth transition chapter. This is a smooth transition chapter. Up till now, we were learning all about sound. Echo, reflection, Doppler effect, everything was associated with sound waves. Now, talking about wave optics, we are going to deal with light waves. Alright? So, we are going to deal with, first of all, let us write down something called as nature of light. Nature of light. Now, whatever we have studied so far, students, whatever we have studied so far, at least do we know that light has a dual nature? Come on students, yes or no? I'm sure every one of us has heard this. That light has a dual nature. Alright? Now, what do you mean by dual nature? Dual nature means that light follows particle theory as well as wave theory. Light follows particle theory as well as wave theory. Okay, Atharv has asked a question. Beta Atharv, is it okay if I explain your doubt towards the end? But just remind me, or else I'll just write down over here. Doubt of Atharv. So I will answer it towards the end. Now beta, just focus over here. Everybody, focus over here. This is a beautiful chapter. And in your NEET examination, you are 100%. You are 100% getting one question from this topic. 100%. And the question is going to be very easy to solve. So 4 marks to minimum you are getting from this topic. They can ask you 2 or 3 questions also. But one to short they are going to ask, and that is an easy question. Okay. So wave optics, talking about nature of light. Light has a dual nature called as particle theory and wave theory. Particle nature and wave nature, because of which light exhibits following phenomena. Few phenomena associated with light. Few phenomena associated with light. Yes, Virat, we are going to study de Broglie's hypothesis later on, beta. Few phenomena associated with light. Now, students, in the chat, I want you all to type very quickly all the phenomena that light can exhibit and that you know about. In the chat, quickly type the phenomena which you all know about, which light can exhibit. I will start with the very first phenomena, rectilinear propagation. Rectilinear propagation of light. Second is reflection. I can think about reflection. Third one is refraction. Reflection, refraction. Have you heard about something called as dispersion? Come on, students, yes or no? We have learned rainbows and everything. Dispersion. Yes, I can think about interference. Then later on in this particular part, we are going to study about diffraction. Interference, diffraction. We will be also studying about something called as polarization, all of you all. Polarization, I'm trying to think. Okay, there's something called as scattering of light. Scattering of light. There is something called as photoelectric effect. And these are few phenomena. These are few phenomena. There are many more phenomena of light. I have just given you all 9 examples. I have just given you all 9 examples to make you all understand that few of the phenomena can be proved by considering wave nature of the light, and few other phenomena can be proved by considering particle nature of the light. Excellent, Aditi. Excellent, Miraj. But basically mirage is because of light waves traveling from rarer medium to denser medium. Any which ways, I don't want to go into those details right now. Right now, I don't want to indulge into those details. Just copy them down. Come on, be quick, all of you all. Yes. Areolis, correct. Atharv, correct answer. In southern hemisphere, we observe that different lights in the sky. Devdatta is asking, sir, is light an electromagnetic wave? Yes, Devdatta, it is. Yes. Okay, students. Yes, moving on. So, students, once again, hope everybody is relaxed and ready to learn something great about light. So, we are starting with wave optics and we have learned about nature of light. All the 9 phenomena that we have discussed, few of the phenomena can be proved by considering particle theory of light, particle nature of light, and remaining of them can be proved by considering wave theory, wave nature of light. Yes, Virat, this is for my reference. I have written doubt of Atharv. That is what I have written over here, so that I don't forget. Okay, this is doubt of Atharv written. Don't worry. Now we are going to study something called as, students, something called as Newton's corpuscular theory. Newton's corpuscular theory. Now, in the 16th century, Newton suggested corpuscular theory. Alright. Yes, Samir, you will have to study particle nature of light in modern physics. You will study particle nature of light in modern physics. Not right now, but yes, before your NEET examination, you will study it in 12th. Now, students, on the board, Newton's corpuscular theory. Write down. Light travels in form of stream of particles called as corpuscles. I have written it on the board, called as corpuscles. By this, what Newton meant was that if we consider a bulb, let's say if we consider a bulb as such, then according to Newton, this bulb is going to emit light in the form of particles. It will emit light in the form of particles. So if we were able to see light particles, then according to Newton, it would look like this. And this light is going to travel, correct? The particles are going to travel. And of course, the light will be emitted in all the directions. And the particles are going to travel. Come on, students, yes or no? Now, can I say that as long as the source is switched on, light will continuously travel, means particles will continuously travel. That's why Newton said that light travels in the form of stream of particles. And he called this stream as corpuscles. Okay. Now, students, what was the advantages of this theory? What were the advantages of this theory? I hope you all are copying this. What are the advantages of this theory? This theory could explain rectilinear propagation, of light. It could also explain reflection, refraction, colors of light. All right. But it could not explain. This theory failed to explain, could not explain. This theory failed to explain the phenomena like interference, diffraction, etc. Is that clear, all of y'all? So basically, later on we can say that this theory was discarded. This Newton's theory was discarded. Why was it discarded? Because it was failing to explain interference, diffraction, all these phenomena. It failed. Come on, have you all copied this, all of you? Done? All right. So, well, if Newton's theory was discarded, there will be some other scientist, there will be some other physicist whose theory will be accepted, and his name was Huygens. Huygens wave theory. Huygens wave theory. Now, many people pronounce this as Eugene. You can pronounce the way you like, but the correct pronunciation is Huygens wave theory. Huygens wave theory. Now, according to Huygens wave theory, every light source students, now pay attention, this is very important. Very important. Every light source produces some disturbances in surrounding medium which propagates at speed of light. At speed of light. Don't worry. I'm going to explain this to you all. So don't worry that what does this mean. But what I want you all to know is, what I want you all to understand over here is, every light source, just memorize this, students. Can you memorize this? Every light source produces some disturbances in surrounding medium which propagates at the speed of light. I'm going to explain this to you all, don't worry. This disturbance, write down, after this write down, this disturbance is called as a wave front. This disturbance is called as a wave front. Come on, students. I'm just giving you all 1 minute to memorize this. I have not explained this, but you all trust me that once you memorize this, understanding part will be very easy. I'm giving you all 1 minute to memorize. Your time starts now. And then I'm going to ask the student sitting on the last bench. Prathamesh Sharma, correct answer beta. Aditi, this disturbance is called as wavefront. I have just explained it like that. This disturbance is called as wavefront. I have not explained wavefront in detail. That I will do right now. That I am going to do right now. Come on, done everybody? Learned? Memorized? Okay. Now understanding part. Before you understand, let us write down what wavefront is. Let us write down what wavefront is, and then with the help of the diagram, I will explain everything to you all. So write down the subtitle. Write down the subtitle as wavefront of a light beam. Write down the title as wavefront of a light beam. Write down, students, write down. It is the cross section. It is the cross section plane. It is the cross section plane. I have written the spelling of plane on the board, beta. It is the cross section plane of a light beam. In which all the particles of medium oscillate in same phase. I have written the spelling of phase also on the board. I have written the spelling of phase. Once again, I'll repeat. It is the cross-section plane of a light beam in which all the particles of the medium oscillate in the same phase. Okay? Now, let me explain everything to you all. Yes, I'm going to ask questions to last benches, beta. So don't talk. All right. Now, all of you all, are you ready to understand everything? See, let us say this is these lines represent plane light beam. These lines represent plane light beam. You understand this? Now, can I say that if I take a particle, if we take a particle somewhere here, I hope this particle is visible. If we take a particle and if we draw a perpendicular to that particle, if we draw a perpendicular line like this, Students, do you remember we have written it is the cross section plane. Cross section plane means perpendicular plane. Cross section plane means perpendicular plane. So students, perpendicular to plane light beam. Perpendicular to plane light beam. Then this line which we have drawn, students, this line which we have drawn is called as wavefront. So similarly, we can have many such wavefronts. Even this line is a wavefront, all of you all. Even this line is a wavefront. So how many wavefronts I have drawn? 3. How many wavefronts I have drawn? 3. Getting it, everybody? We have drawn 3 wavefronts. Chalo beta, all of you all focus over here, beta, not in the chats. Okay, focus over here. So we have 3 wavefronts. Now what is the specialty of this wavefront? What is the specialty of this wavefront? The specialty of this wavefront is that all the particles of the medium, all these particles that I'm highlighting, all the particles are going to be in the same phase. All of them are going to be in the same phase. Once again, all these particles, 1, 2, 3, 4, 5, 6, all of them are going to be in the same phase. We have drawn 3 wavefronts over here. These dotted lines are wavefronts. Don't worry, I'm going to explain you all one more. Don't worry, I'm going to explain one more. First, copy this down. Copy this down. Prathamesh, beta, correct answer. Prathamesh Sharma, keep it up. Are you all done copying, everybody? Nisha, I didn't understand your query. Can you please ask again? Okay. Let us understand one more thing. Let us take one more example to understand it. Let us say we have diverging light beam. We have diverging light beam. This is diverging light beam. Okay, diverging light beam. Yes, Harshal, Nisha, both of you all, whatever doubts you have, it will be cleared in this part. Pay attention on this part. Because if you understand this, you will understand plane. So pay attention, you will definitely understand this. Now, this light beam is of diverging nature, like this. This light beam is of diverging nature. Then what you do is, we can mark 6, 7. There is no lag, Nisha, there is no lag. We have marked the particles. What is the specialty of these particles? All these particles are in same phase. All these particles are in same phase. Do you understand this? Once again, I've drawn wavefront like this. So all the particles that I'm highlighting over here are totally in the same phase, and they're perpendicular to the light beam. Wavefront is perpendicular to the light beam. Understood this? So Nisha, it is not parallel, it is perpendicular. Such a wavefront is called as convex wavefront. Convex wavefront. We are going to observe the wavefront from the point that we receive the light. That is, we are going to observe the wavefront in front of propagation of beam. This is a beam, na beta? This is a light beam. These are light beams. So we are going to observe it from the front. So from the front, which shape is this? Convex wavefront. Come on. Is it clear, or you want me to give one more example? Is it clear, or you want me to give one more example? Tell me. Okay, students. If it is clear, then I'm going to ask you one question. Beta. Let's see how many of you are able to answer this. Right now we had done diverging light beam. So now I'm going to take an example of converging light beam. Like this. These are converging light beam. Let me write it over here. So tell me, students, that if we are going to observe the wavefront from this end, what will be the shape of wavefront? Convex or concave? C shape. Excellent, Aditi. Excellent answer. But I want the answer in terms of convex or concave. Yes. Sara, Sakshi, Prachiti, Aditi, correct answer. It will be concave. Correct. Like this. So now I can confidently say that you guys have understood this. Tell me, what are the specialties of these points that I have marked? What are the specialties of these points that we have marked? All the points are in... Yes, nice answer, beta. Same phase. All the points are in same phase. Correct answer. Correct. So I can say this is nothing but a concave wavefront. This is nothing but a concave wavefront. Copy it down quickly. All right, done copying? So based on this, we are going to study three types of wavefront. We are going to study three types of wavefront. First one is plane wavefront. Second one is spherical wavefront. Third one is cylindrical wavefront. Yes, Virat, correct answer. Spherical, cylindrical, and plane. Just write down after these three. Write down in the bracket. Depends on the nature of source of light. Depends on the nature of source of light. We are going to discuss about them in details later on, not right now. I've just given you all the names. Later on we'll discuss the details. Now I'm going to explain it to you all. Since now I'm going to explain to you all a very interesting topic. Huygens theory of wavefront propagation. We are going to study Huygens theory of wavefront propagation. Okay, what do? We'll first write down and then we'll understand it. So write down. Every point on a wavefront, every point of a wavefront, every point of wavefront in a light beam acts as a source of new disturbance, acts as a source of new disturbance in surrounding called as secondary wavelets, called as secondary wavelets. Yes, Harshal, I'm repeating again, guys. We are studying Huygens theory of wavefront propagation. Every point of wavefront in a light beam acts as a source of new disturbance. Acts as a source of new disturbance in surrounding called as secondary wavelets. Continue. These secondary wavelets produce their own spherical wavelet. Students, 1 second, hold on. I'm going to read the second line. 1 second, hold on, guys. Yes, now just check what you have written. These secondary wavelets produce their own spherical wavefront. These secondary wavelets produce their own spherical wavefront. And the common tangent of these wavefronts gives the next position of previous wavefront. Gives the next position of previous wavefront. Now, students, this statement seems to be slightly challenging, but trust me, like last time, you will understand everything. I'll explain each and every word written, but before that, what will you do? You will just learn it. There are some parts to which first you learn, and if you then understand, everything fits properly. 1 minute, your time starts now. Take your time, beta. No problem. Take your time. I'm going to explain this with the help of a diagram. Let me know once you are done. Okay, it's time to understand this. It's time to understand. Okay, Aditi is saying wait. Aditi, I'm just going to give you 1 more minute. Okay, now students, let's understand this. These are nothing but plain light beam. This is nothing but plain light beam. Okay. Now I am going to draw, or I am going to take particles of the medium. I am going to take particles of the medium and I am going to join them with a straight line. I am going to join them with a straight line. All these particles are in same phase. All these particles are in same phase. Then what will you call this line as? Students, what will you call this line as? Correct answer. You will call this line as wavefront. Yes, nice, nice. Keep it up, all of you all. Correct. Now, students, all the particles which are in the same phase, in that, let us say, I am considering this particle. I am considering this particle. Then what does the Huygens theory tell us? What does the Huygens theory tell us? That every point on the wavefront, every point on the wavefront is going to behave like a new disturbance. So this point is a new disturbance. Similarly, this point is a new disturbance. This point is a new disturbance. This point is a new disturbance. Every point is a new disturbance. What did Huygens tell us? That every point is a new disturbance. And this new disturbance will produce their own spherical wavefronts. So this is a wavelet, this is a wavelet. And all the wavelets are going to produce their own spherical wavefront. Once again, dhire dhire, once again. This is a wavefront. This is a wavefront. Okay? Now all the particles of this wavefront, are referred as new disturbances called as secondary wavelets. Secondary wavelets. So what is this? Secondary wavelet. What point is this? Secondary wavelet. Secondary wavelet. All these points are secondary wavelets. Fair enough? And why do we call them secondary wavelets? Because they are going to produce their own spherical wavefront. They are going to produce their own spherical wavefront. So if I talk about this particular wavelet, it will produce its own wavefront like this, spherical wavefront. Once again, if we consider this wavelet, it will produce its own spherical wavefront like this. Anywhere you can consider, correct? If we consider this is a wavelet, secondary wavelet. It will have its own spherical wavefront. And then it says that if you draw a common tangent, like this, if we draw a common tangent, straight line, if we draw a common tangent, then these are once again, this is nothing but locus, and this locus is called as once again wavefront, correct? This straight line is once again a wavefront. It is collection of all the points in same phase. It is called as a wavefront. So initially the wavefront was over here, then the wavefront is over here, then the wavefront is over here. So it is giving the next position of previous wavefront. This is the previous wavefront, correct? This is the previous wavefront. And this second line is going to be the next position. I know it's getting difficult, but that's the reason I'm going to give you one more example. Okay, Nisha is asking us a question. Are spherical wavelets similar to wavefront? Then how to distinguish between them? Nisha, generally wavelet is a particle, is a point. Generally wavelet is a point, source, point, generally. And this spherical are wavefront. This spherical is a wavefront. And tangent gives us wavefront of the previous wavefront. Next position of the previous wavefront. Can I take one more example to explain you all? Can I take one more example, all of you? Come on, yes or no? All right. Pay attention. On the board, pay attention. This straight line is a wavefront. Now you just focus on this part. This second straight line is wavefront. Let us name this as wavefront number 2. And this is wavefront number 1. Okay, so I'm just talking about the second line now. Now this second line, can I say it is going to have infinite points of the medium in same phase? Just focus on the second line, students. It is going to have infinite points of the medium which are going to be in the same phase. You consider any points. Let us say I'm going to consider this point. Then this will be called as secondary wavelet. This is called as secondary wavelet. Even this is a secondary wavelet. Even this is a secondary wavelet. All these are secondary wavelets. Now what will these secondary wavelets do? They will behave like a new disturbance. Secondary wavelet is going to behave like new disturbance. New disturbance means new light source. New disturbance means new light source. So what will it do? It will produce spherical wave front. This is a spherical wave front produced by secondary wavelet. Talk about this. This is a spherical wave front produced by secondary wavelet. This is a secondary wave front produced by secondary wavelet. This is a secondary wavelet. And now what you do is you draw a common tangent. You draw a common tangent, a straight line like this. Then this will be called as wave front. This will be called as a wave front. Yes, Nisha, correct. Second wavelet is formed on wavefront and they decide the next position of wavefront. Correct. You have understood it thoroughly, Nisha. Now guys, just copy this and I'm going to take a new example. I'll erase and I'm going to take a completely new example. Then let's see whether we are understanding it or not. Okay, so now I'm going to take next example of tell me if I'm drawing light beams as such. If I'm drawing light beams as such, what are these light beams called? These light beams are called as, correct answer, diverging light beam. Diverging light beam. Ekta is asking definition of wavelet. Ekta, in above paragraph you have already written what wavelets is. Now we just need to understand that English statement that we have written. Okay, so we have already written in technical terms what a wavelet is. Now understand it on the board with me. Are you ready now? Let's start. So this is a diverging light beam. Let us mark a wavefront like this. Let us mark a wavefront like this. So this wavefront is made up of infinite particles, infinite medium particles which are in same phase. Infinite medium particles which are in same phase. Got it? Now, on this, let us name this wavefront. Let us name this wavefront. I will call this wavefront as Mr. X. What is the name of this wavefront? The name of this wavefront is Mr. X. Now, on this X wavefront, you can mark particles anywhere that you like. Anywhere that you like. So let's say I'm going to mark particles such that it is easier for you all to understand. It is easier for you all to understand. I have marked the particles here. Alright? Now, all these particles will be called as secondary wavelets. So what is this? Secondary wavelet. What is this? Secondary wavelet, secondary. All these particles are secondary wavelet. What do the secondary wavelets do? Secondary wavelets will produce their own disturbances. They are going to behave like source. They are going to behave like source. So it is going to produce their own spherical wavefront. So wavelet produces spherical wavefront. I'm going to erase it, otherwise it will be confusing, but just remember this. So let's draw. This is a spherical wavefront. This is a spherical wavefront. Similarly, this is spherical wavefront produced by wavelet. So everywhere will have such spherical wavefronts. Okay. Now what you do is you draw common tangents. You draw common tangent. So when you draw common tangent, it is going to look like this. When you draw common tangent, it is going to look like this. So what is this? This common tangent is nothing but group of those particles of the medium. It is group of those particles of the medium which are in the same phase. So even this is a wavefront. And Mr. X was over here. Then this line is going to represent the next position of Mr. X. This line is going to represent the next position of Mr. X. Got it? I hope this is clear now. The concept of wavefronts and wavelets. Come on, students. Let me know in the chat. Aditi is writing, okay, sir. Yes, sir. Crystal clear, sir. Understand very clearly. Okay. So I believe that all of you all have understood. If you all have understood, then I will ask all of you all one example. I'll ask you all one example. Are you ready to answer the question? Are you ready to answer the question? Okay. So the question is that, guys, now I'm going to take convergent light beam. Now I'm going to take convergent light beam. That is convergent light beam. Convergent light beam. And now we are going to observe it from the point where we are receiving it. We are going to observe it from the front. And from the front, we are going to obtain a concave wave front. We are going to obtain a concave wave front. Let us say name of this wavefront is Y. Let us say name of this wavefront is Y. Now I'm going to ask you series of questions, and if you are able to type it in the chat box, I'll be reading your answers. So first question to you all. First question. This is a concave wavefront. What is this concave wavefront made up of? That is the first question. What is this concave wavefront made up of? Let's see who gives the correct answer. I'm waiting for your answers. Yes, I got few answers, but that is not the answer which I'm looking for. That is not the answer which I'm looking for. I'm receiving multiple answers, but that is not the answer. Virat has answered. Virat Rajput has answered that infinite particles. What can you say, Virat, about these infinite particles? Prachiti Gaikwad, perfect answer. First student to give perfect answer. What Prachiti has written? She has written infinite medium particles in same phase. Correct. This concave wavefront consists of infinite medium particles in same phase. This is the answer which I was looking for. Okay, so first question, only one student got it correct. To the point, only one. Infinite medium particles in same phase. Alright, now all of y'all get ready to answer second question. Second question coming up. If this concave wavefront is made up of infinite medium particles which are in same phase, so if I mark particles randomly anywhere, if I mark particles randomly anywhere that you want it to be, what are these marked particles called? What are these marked particles called? Yes, now everybody is answering correctly. Secondary wavelet, that is correct answer. Yes. All these marked particles are called as secondary wavelets. Now, students, third question. Third question. What will this secondary wavelets do? What will this secondary wavelets do? Yes, Devdatta has answered it. Very good, Devdatta. So the answer is these secondary wavelets are going to produce their own disturbance in the form of spherical wavefront. What is the correct answer? These secondary wavelets are going to produce their own disturbance called as spherical wavefront. Correct answer. Yes, I can see all of you have answered correctly. Keep it up, guys. So this is a secondary wavelet. Oh, sorry, this is a new wavefront, new spherical wavefront. This is the new spherical wavefront. This is also a new spherical wavefront. Like this. Now, fourth question. After drawing these spherical wavefronts, what are we supposed to do? After drawing these wavefronts, spherical wavefronts, what are we supposed to do? Correct answer. Draw a common tangent. Nice. We are supposed to draw a common tangent. And the common tangent is going to look like this. Common tangent is going to look like this. Common tangent. Now this common tangent when we join all such particles of the medium, when we join all the particles of this medium to draw a common tangent, this entire common tangent will be collectively named as fifth question. Fifth question. This entire common tangent will be collectively named as, correct, wavefront 2. Excellent. Keep it up, guys. Wavefront 2. And this wavefront is position. Yes, Dev Datta has answered it again. We'll give the next position of previous wavefront. See, this was the previous wavefront. This is previous wavefront. This. So this previous wavefront, next position will be drawn over here. Next position will be drawn over here. Now let me know whether you have understood the three examples or not. Let me know whether you have understood how the wavefront and wavelets work. Yes. Alright, so since I am getting positive replies and correct answers, I want you all to copy this down and then we can start with the next topic very quickly. Okay. Now we are going to move on to the next theoretical topic, which is Maxwell's electromagnetic theory. Maxwell's electromagnetic theory. It is most popular and useful. Write down, it is most popular and useful. Second point, students, this Maxwell electromagnetic theory was very useful in understanding the wave nature of light. Is very useful in understanding the wave nature of light. Now write down. Light, second point, write down. Second point, light energy is a wave. Light energy is a wave light energy is a wave. Guys, pay attention. Light energy is a wave which is electromagnetic in nature, in which electric field and magnetic field. I have written it on the board. Electric field and magnetic field oscillate simultaneously. In planes perpendicular to direction of propagation of light. Perpendicular to direction of propagation of light. Now I can show you all how the electric field and magnetic field vectors look like. We can understand it like this, that if this is electric field vector, then magnetic field vector is going to be perpendicular to it. Magnetic field vector is going to be perpendicular to it. So this is electric field vector and this is magnetic field vector. I'll explain it to you all. The vibrations of electric field, if they are vertical, then vibration of magnetic field will be horizontal. Now I cannot draw horizontal like this. Okay? That's why I have to draw it slightly inclined. I'll explain it to you all again. Students, have a look. If this mobile represents electric field vertical, then this is going to be magnetic field. Electric field. The wave will be drawn like this. Like this, vertical. Then this is electric field. Now this is magnetic field. This is going to be magnetic field where wave is drawn like this. I hope you understand that. Both are perpendicular to each other. Is that clear, everyone? So it's basically like this. If you look at my fingers, if the first finger represents electric field, then my thumb represents magnetic field, and the middle finger represents the direction of propagation. All the three are mutually perpendicular. Electric field, magnetic field, and direction of motion. All the three are perpendicular. Like this. First finger, electric field, thumb, magnetic field, middle finger, direction of propagation. And remember a relation that electric field is speed of light times magnetic field. Important relation. Electric field is speed of light times magnetic field. And amongst the two, electric field is the one that is useful for sensation of light. We can sense the light, see the color. That is because of electric field. So what is magnetic field used for? Magnetic field is used for propagation. Magnetic field is used for propagation. This is nothing but Maxwell's electromagnetic theory. This is called as Maxwell's electromagnetic theory. Now tell me, is this part clear to you all? Out of electric field and magnetic field, majority of the times electric field is quite essential for us to study. And the formula is quite simple. Electric field is equal to C times magnetic field. Electric field is equal to C times magnetic field. All right. Then we'll end the lecture here. Next lecture, you all revise this concept of wavelets and wavefronts. And I'm going to start asking everybody, especially the guys sitting on the last bench. I hope you all understand this. What is C? C is speed of light. C is speed of light. C. And before we end the lecture, I am able to see Atharv had given us a doubt. So is Atharv still here? Yes, Atharv, I am going to answer a doubt. But unfortunately, I don't have the question with me. Type the question again, quickly. Atharv, type the question. Okay, Atharv has given us the question. So let me quickly answer the question. Says tuning fork F1 has a frequency of 256 Hertz and it is observed to produce 6 beats with another tuning fork F2. Okay, 6 beats. It is giving us 6 beats. 6 beats. It means that value of this tuning fork can either be 250 Hertz or it can be 262 Hertz, correct? Difference of 6 beats. When F2 is loaded with Vex, this is F2 loading with Vex. It still produces 6 beats. The frequency before loading is. Okay. Now students, tell me, what do you understand by loading? Loading means you are applying Vex. And just remember that whenever loading takes place, frequency decreases. Frequency decreases. Understood? So after loading, let us say the frequency is n. After loading, the frequency is n. And the number of beats given to us is 6. If you read the question, number of beats given to us is 6. So students, the question says tuning fork 1, tuning fork 2. Tuning fork has a frequency of 256 Hertz. Tuning fork 2 has unknown frequency, but it produces 6 beats. So we have written two values, either 250 or 262. Now we are loading this tuning fork. But number of beats remain the same. So what is this frequency? Whether it is 250 or whether it is 262, that is what we have to understand. Got it? Now what does loading mean? Loading means frequency decreases. It becomes heavy, na? If you apply Vex, the tuning fork becomes heavy. If it becomes heavy, then frequency decreases. Alright? Frequency decreases. So, think about this. If at all you are saying 250 is the answer, so tell me students, if you perform loading on 252. If you perform loading on 250, the value will decrease further. From 250, it will become 245, it can become 240, it can become 230, any value it can have. Tell me, will the difference be 6? Not possible. Will the difference be 6? Not possible. Okay. So in that case, 250 is not the correct answer. 262 hertz. 262 hertz. 262 hertz, if you perform loading, then value will decrease. So from 262, it can become 260, it can become 258, it can become 250, it can become 245, any value it can attain. And now tell me, 256 and 250 will give us 6. Will give us 6. So the correct answer is 262 hertz. Correct answer is 262 hertz. Did you understand this? All of you all? So that's it. End of the lecture. Any other doubts, all of you all? Alright, then I'm ending the lecture over here.